Us here today. So Wahid is local, but has a really wide background. I guess he started his journey in PhD in high energy physics, and since then has done a lot of work in scientific computing. Wahid is the division deputy for AI and science at NERSC, and as part of this role, I guess has led multiple initiatives in terms of deep learning at scale, deploying generative models and probabilistic programming for a really wide range of science applications. I guess these days, this work continues at NERSC with various clusters. And so, yeah, I'm really looking forward to Wahid's perspective and a talk on transformative AI for science and on super.
Yeah, I had to have an impressive
welcome, Wahid.
Thank you. Thank you. Thanks for having me. Thanks for the introduction. Yeah, so I'm Wahid. I'm at NERSC up the hill. You can see, well, you can't quite see yourself down below this picture because it's blocked by the massive building, but you can certainly see us from here or from nearby. Okay, so in this talk, I wanted to kind of cover broadly kind of what NERSC does. I know a lot of people are potentially interested in using NERSC systems and in the kind of work we do. So I wanted to kind of cover that. But then I also wanted to cover like a few like specific projects. And so I've kind of split this up into talking about science collaborations. And so there I'll talk about more deep engagements that we have, and in particular one science project, OmniLearned. But then I'll also talk about broadly how you can access NERSC and how we help the community. Then I would focus a bit more on the HPC side, high performance computing, and how supercomputers can help AI for science. So again, broadly how we see that at NERSC, but then some more in-depth stuff on performance modeling. And then generally talking about the importance of data in AI for science. I'm sure you know that. But then some work we're doing around benchmark and benchmark platforms and some specific competitions that we have open at the moment as well. Okay, so just stepping back a minute, NERSC, we're up the hill here, as I mentioned, located in Berkeley lab, but we're actually a national facility. So we call ourselves the Mission High Performance Computing Center for the Department of Energy Office for Science. So that means we support the broad workload of DOE, like, earth sciences, materials, high energy physics, fusion, etc. So we have over 11,000 users, we have thousands of projects. But then the HPC part of it is that we deploy large compute systems. So Perlmutter has over 7,000 A100 GPUs, and that's since 2021. So it was actually the largest A100 system at the time. Of course, now in industry, there's these giant systems. So we're no longer the biggest, but we're still an incredible resource for science. And alongside that, we have lots of data infrastructure as well, and like tape archive that hosts loads of data that isn't available anywhere else. But, we're evolving. So I'll talk a bit more about this. We're already planning for our next machine, Doudna, which is coming at the end of 2026. Yeah, I'll talk about this in a minute. And then we're also looking to the future. But then in terms of the AI space, kind of what we do, as I said, core to what we do is deploy these large systems, and also work to make them, optimize, working with vendors, and then, software, etc. on top of that. But then we've also felt a need to apply directly AI for science and work with communities, and I'll talk a bit about that then. But then we really want to build those experiences into the wider ecosystem. And so we run lots of training and tutorials and schools. So I often say NERSC is at like the nexus of AI for science, in that, we've heard that what's important about making modern AI work is access to large data sets and large compute. So we have that. But then we also have deep connections with the scientists. And I think particularly in science, that's important because, it's not just a data crunching exercise. And then we've built up over time AI expertise, and particularly in making use of big systems for these workloads. Okay, so just to talk about some AI collaborations at NERSC. So as I said a number of times here, we do deep engagements and then we build that into broad impact. So particularly in the deep engagements, we've had this program called NESAP, NERSC Science Acceleration Program, that's allowed us to have postdocs working directly with scientists. And this is like a competitive call. Actually, we just had one recently focused on Doudna, the next system. So we've actually selected those teams now, but if you want to put in proposals for future participation, that's an area where we can directly work with you. So some of these deep engagements at the start of Perlmutter, I won't go into these projects in detail, but right at the start of Perlmutter, we really saw, I think, a change in how AI was applied to science. So just to give a few examples here, ForecastNet was a project working with NVIDIA and Caltech to forecast global weather at high resolution. And this was perhaps the first model that achieved the skill of numerical weather prediction with an AI model. So that's a huge landmark, and it's led to several works after this. So Google have their model, ECMWF, the weather center in Europe, now has their own model that's actually state of the art. But the point of these is you train them at large scale on Perlmutter, for example, but then once you actually have a model, it's tens of thousands of times faster to do a prediction than numerical weather prediction. So this is really opens up a new avenue in the field. And so similarly, we've had projects in catalysis and in high energy physics, and I won't talk about these because I'll talk about more in a minute. But if you look at the evolution of these projects to now, I think we really see that the kind of it's moved in various directions. For one thing, a lot of those projects were led maybe by computer scientists or by NERSC. Now we really see a lot of them led by domain scientists. So, for example, this Huge Ensembles project is led out of actually LBL Earth Sciences. And there the idea is to use a model like ForecastNet. And because it's so much faster, you can run huge ensembles of predictions and use that to take different climate scenarios and look at the potential extreme weather events that lead from those. So I think this is pretty exciting. On the molecule side, so Brandon Wood, who may have come to talk to you, or I think you had other people from Meta come back. He was a NERSC postdoc in the first round of NESAP postdocs that we had. Now works at Meta, and him, together with, again, domain scientists at the lab, put out this data set, Open Molecules. I think you had a presentation about it a few weeks back. And this is now the basis of this universal model for atoms, which is moving towards this idea of foundation models. And then similarly, we've seen the idea of foundation models in particle physics emerging. And so this project in particular, OmniLearn, I'm going to talk a bit more about. So OmniLearn, which is mostly driven by Vinicius, who was a postdoc with us and now recently moved to Japan to take up a professor position. So just the setting for particle physics in general, you've probably heard this multiple times from different speakers, but the Large Hadron Collider at the Swiss-French border is a city-sized particle physics collider, which smashes together protons inside a building-sized detector that has hundreds of millions of channels, records every 25 nanoseconds. So creates a huge volume of data. That data is difficult to interpret because, for example, if you have a particle produced that is affected by the strong nuclear force, it will produce a whole spray of particles. These are called jets. So you might have a top quark fundamental particle produced, and that leads to a top quark jet. And that kind of produces this signal in the detector from which you want to do various things. So, for example, you might want to do all these things that they call in the community jet tagging, which is actually a classification of what the jet was. Or you might want to do anomaly detection, looking for unusual particles that you didn't know what they were ahead of time in this data. Or you might want to do, a lot of this, or a lot of studies are done by comparison of simulated with experimental data. So vast volumes of simulation need to be made. And so you might also want to use machine learning to accelerate the simulation. So these are both supervised and unsupervised tasks. Machine learning has been used in these for quite a while, and in particular, even deep learning has been used for at least a decade or around a decade, but often with specific networks for all these different purposes. So Vinicius, who's worked on several of these projects across different domains and had all the data sets, managed to come up with the idea of how do we build a single model that can do both supervised and unsupervised tasks. So that he might have even presented here before on that, but new last week, he, and I guess we, because he was kind enough to put me on the paper, even though I didn't do anything, put out a new version of OmniLearn that really takes this a step further to really large scale models. I think it's really achieving what foundation models can achieve in language models, for example. It's moving towards that idea of building a bigger model. Okay, so I'll go through a few details of this project. So OmniLearn, the architecture, which was kind of in here, is a standard body, as you might expect, with a foundation model with different heads for the different tasks. So the core of this is this point edge transformer, as you described it. Now, I think you had a talk last week that also talked about point edge transformer for materials or molecules. I wasn't at the talk, but I think that's just a coincidence that it has the same name. It isn't actually the same exact architecture, but it is very similar. And I think the intuition in both is that this data is continuous and best represented by a point cloud. So to combine graph neural networks with transformers rather than the language model kind of tokenization of data. So then you have this embedding that takes particles and in this main body, but then you have these different data sets that have some information or don't have some information, depending on the data set. So for example, they might have particle ID information only in a certain amount of labeled data sets. So then you do data set specific embeddings, like kind of like dropping randomly some of this kind of like dropout to get a representation that works across both features. And then you have these different heads for generators, where you want to condition on the class that you want to generate, and a flow matching kind of architecture, and flow matching loss is used for that diffusion model. And then classification output that can use these various tokens to predict the jet type. So this is a basic architecture. The other key part of this work is to actually build a huge data set, so a billion jet data set. So like in many fields, actually, there's huge data sets out there, but they're often used separately and not put all together in one giant data set. And they may have various reasons for that, like they're not AI ready, for example, or provided in a single format. So Vinny diligently, put together all this huge data set and was able to, store it in NERSC, because we have the ability to pull data sets as well as compute on them. So it's kind of, well, you can look up all these data sets, and many of them have, they're well curated, but putting them together really allows you to kind of go a step beyond that. And so all this data is, of course, made available for others to use as well. So then OmniLearn manages to achieve state-of-the-art performance across different tasks. So for example, this top tagging, which is identifying top twats as a classification task, is kind of well-explored field. So this plot is showing the inverse of the background efficiency. So how much background you can get rid of at a fixed point of how much signal that you're interested in. So you want to be higher in here. Across by publication year. So there was, even in 2018, there was a huge amount of deep learning models put out there to solve this problem. Then these have gone a level above with all kinds of like LorenzNet that maybe built in some physics intuition. But then there's been a step above that from various models that are pre-trained. So using this idea of foundation models to get better performance. And you can see OmniLearn achieves state-of-the-art of there. And then also the fact that different sizes of the model show increasing performance. So here you're perhaps seeing, like we've seen from language models, that you can actually benefit from more and more data with larger and larger models. So it's not like we've done the full neural scaling analysis here, but you can kind of see the same idea coming out. But then also for anomaly detection, which is a bit more unusual task, I don't think it's going to be possible to explain these plots. But the point is that this is like a kind of existing method, and this is OmniLearn, and this little bump shows that this particle that's in the data, but it wasn't explicitly trained to find, can be identified by using this approach. And this is actually using open experimental data, not simulated data. So it's kind of exciting that one can go back to open data and find kind of new things or anomalies. Okay, so that was explaining that project. And in all of these, I guess I haven't had time to explain them in that much detail, so I will be around a little bit afterwards if you want to talk more on these things. But we build this broad impact, and that's done in various ways. For example, we have calls for compute time that allow us to reach more projects than we can work directly with. But then we also want to reach out to all NERSC users and then even beyond NERSC users to the wider community. So in terms of this compute time allocation, we saw this growing maturity. I should probably mention that most of the compute time at NERSC is actually given out by the science program offices. We don't directly control it, but we do have a certain amount of time, 10%, that is directors can reserve. And we use that for strategic projects. And since we saw there was this need for, AI for science for compute, we put out this call, and we got like 40 teams in 2024, another 50 teams in 25, and we will have this call again in 2026. So we have hundreds of applications demand across organizations. I mean, there's Berkeley Lab and Berkeley campus here, but a large amount of applications from MIT as well. And there's been kind of dozens of papers resulting from this. But again, if you look at the highlights, a lot of people are really using the resource to train larger models and open sourcing those models. So the kind of point we talked about actually over lunch, that people are actually now making these available, and that can provide like AlphaFold-like models that are more accessible for other people and tuned towards different structures described here. So that's just the program that we have. But then we have also programs for community engagement. So just to give a bit of an advertisement for this school we have. So we had up at the Hill, one in 2025, and all the lectures are online. And we try to invite people from industry who are actual practitioners and use these models in practice and give practical talks. And actually for 2026, we're probably going to host it here because it's a bit more accessible. We don't have to get everyone up on the left. And then we also run this event, Deep Learning at Scale tutorial. And I think this is a little bit of a unique event because it really focuses on how do you scale these models in a generic way. So some things like language models, you can just take an off-the-shelf implementation that works well across multiple GPUs. But if you're trying to scale your own science model, data parallel or model parallel, then that's quite challenging. And these lectures can hopefully give you some tips to do that. And we run this jointly with NVIDIA. So they have a nice piece that gives you kind of performance analysis, kind of in-depth material. And again, we make all the material available. This is held at Supercomputing, and so it is upcoming. But if you don't want to pay, you can just look at the detailed README, or we run this also at NERSC as well. So. Okay, so the next section I was going to get to, a bit of a change, is in the use of HPC for AI for science. So in general at NERSC, we can look at the workload and we can see that there's a huge amount of increase of interest in AI. So the left one is just projects that say they're doing machine learning generally. That's risen to like 30% from 4% back in 2018. We also directly catch people who import PyTorch or TensorFlow when they run at NERSC. And here you can see, for example, that over 1,200 people are using PyTorch in 2024, when there was 0 in 2017. So there's a huge increase in that. We also run surveys, so we can track the community from that. And I have a link to slides with more details. But for example, we ask the types of models. And you still see that people run a lot of, CNNs and fully connected neural networks. So it's not like transformers have taken over everything, but they certainly have grown recently in their usage. We can ask people what they're doing, and it's interesting to see that people are trying to couple machine learning with traditional scientific simulation. So, that's actually a unique need in science, maybe. And then also we can see that people are doing distributed training, data parallelism, model parallelism. We have other questions about the scale at which people are using. So there's interest, as you'd expect perhaps at NERSC, of people to train large models. So in training large models, I think it's important to worry about performance. So we had this kind of paper and study that went into more depth on how to model performance. So the setup here, as I said, transformers are increasingly used in science. But the way they're used can be different to how they're used for language models. So for example, Oh, well, this is saying the same thing. For example, if you have a high resolution image, something like weather climate prediction that I described before, and you use a vision transformer to that for that, and it's a global high resolution image, then you might have a lot of tokens in here, which actually changes the relative balance of the compute used in self-attention compared to the MLP part of the transformer. And it's a lot less well understood, obviously, than large language models. And even a small model in terms of parameters, it's not just about the parameter count. A small model with a large input can be as expensive as a trillion parameter large language model. So there's a need to understand costs and bottlenecks, I think, and understand the sensitivity of performance, particularly with respect to parallelization strategies, like do I want to make this data parallel or model parallel? Which of these regimes am I in, science or large language models, my hardware, and the scale in terms of compute resources. And we saw this as a value add both for users who can get some insight as the optimal way to parallelize their models, and maybe do an architecture search that actually has that performance in mind, because they don't necessarily want to, well, it's obvious, I guess, as well as for us for designing systems. And so particularly for designing our next system, NERSC 10, we can get insights into what are the correct balance of where do you spend your money? Is it in fast networking? So NVLink is mentioned here. This is how you connect together. Currently on node, GPUs are connected together. So on Perlmutter, we have 4 GPUs on a node. Those are connected with NVLink. And then across nodes, it's connected with something like InfiniBand, or in our case, Slingshot, which is still a fast network, but not as fast. But in the future, you can connect together even nodes with NVLink, but that's quite expensive. So how do you create that balance?
So
Yeah.
Traditionally, in the old time, HPC was always CPU. So one would say HPCs versus GPUs. Can you comment a little bit on how this boundary has been fluent, how much people do HPC compute on GPUs rather than CPUs?
Yeah.
You have this Perlmutter nodes which have both CPUs and GPUs. So
right. Yeah. So, I mean, I think so Perlmutter has both CPU only nodes as well as GPU nodes, which also have CPUs on them. And at the time, so, I mean, I can briefly go back. Oh, no, that will take ages, but so our previous system, Cori, which is around where I joined, was just a CPU only machine and went more to many core CPU, like Knight's Landing machine. And part of the reason for that is we didn't feel that the science community was yet ready to make use of GPUs. So when Perlmutter came in, we had both these GPU node types, and there was kind of a lot of debate about the relative size of these two partitions. And there was a lot of prediction that at the time I thought was optimistic about how much of the just traditional scientific workload would move to GPU. As it turns out now, we do find that so we have about we have about the same number of nodes in CPU and GPU, right? But the GPU nodes are generally the more popular now. And, it happened that this came about with the rise of AI as well. So that's one thing. But then we also see that, for example, material science codes like fast runs on GPU, increasing.
I would just ask for CPU and you give it to me. Resilience for GPUs I want.
Well, at the moment, it might be easier to get a CPU allocation than a GPU allocation. I'll tell you that, although I guess it's on the record now. But of course, you're getting a lot less compute. So even though we have an equal number of nodes, the vast volume of the actual flops is all in the GPU. So if you actually want to get a lot of compute, it depends whether you can make use of GPU or not. But we're doing this analysis again for NERSC 10. So we will have some CPU only capability in NERSC 10 as well. But we've really seen that the community has moved quite a lot. So I would expect that if you want to see increases in computing power, you have to adopt GPU, really. And that's part of the end of Moore's law, etc. We've been saying for a while that you have to move to new architectures to. Okay, where was I now? Oh yeah, system modeling. Yes. Okay. So performance modeling for AI is kind of challenging because there's a huge design space. So you can change your parallelism, or you could change the architecture of your model, how you ran it, or you could change your system. If you allow all of that to be free, you've got a huge space, right? So we built this kind of performance model. So this is actually just a simple analytical model that allows you to take all these inputs and search over the entire design space. So often when you see, oh, this machine will be better than that, they don't take into account the fact that you could run the model differently on the other machine. So we do a kind of search over the whole space. Then we kind of break down the detail, arithmetic intensity and overheads. And then from that, you can predict an optimal parallelization strategy, where your bottlenecks are, or what system would work for you. Okay, so just to give kind of the kind of output you can get. So one is just a high level overview of the scaling behavior. So if you take one of these models, like a science transformer, that's basically doing a transformer on large scale kind of weather-like images. And you look at the training time in days, so you know, lower is better, and this is a log scale. So this is 1,000 days, so basically intractable. And this is like, you know, 1 day. These are different architectures. So you can see that moving from the A100 system that we have in NERSC at the moment to the kind of Blackwell systems that are available now, you get quite a significant, you know, performance increase. And obviously running on more GPUs, you get that. But then you can also look at, like, do we get this NVLink, which, as I said, in the future, you'll be able to connect together multiple nodes with this NVLink. So you can build bigger and bigger sizes. So what we currently have is 4 GPUs tightly connected together, but you can spend more on that. And then you can basically see the effect of this. And if you actually look, I just showed one plot here. If you look at LLM kind of transformers, you don't actually see much benefit from using NVLink, large NVLink sizes, unless you go to very large scale, and then you can see it. For a science transformer, it's actually different. You can see benefits at all kinds of scales, but whether that's worth it depends on the cost, which isn't factored into it.
That's the question.
Yeah.
So when you say science, for example, you just talk in past mentioned weather. So
Yeah.
is that specific to weather? What if I want my transformer for nuclear physics? Or what if I want it for my CERN experiment?
Yeah.
What if I want it for material science?
So the basic model here is any kind of vision transformer with high resolution images. So we don't directly put a weather model into this, right? We just have the idea of running on images. And we actually see that quite common across different domains. So I'll mention in a bit that there's this new DOE AI initiative, the American Science Cloud, and actually the number of the model teams for that across different science that are intending to make use of vision transformers is, quite large. So for example, fusion experiments, you can model a high resolution image as the fusion, so they're interested in it. The light source people, they do segmentation on large images coming from light source data. So these kind of findings would be pretty similar for any of those domains.
They're all vision-based.
They're all vision-based, correct. Yeah. Yeah, absolutely. Yeah. So the performance model, that we've open sourced would allow you to change that kind of thing and rerun, right? We only made plots for 2 kind of cases. One was like a language type model. And so if you used, for example, sequences for protein, and that was your science transformer, and it was very large language model like, then you could use that plot. But if you had a whole different setup, then you would have to reuse the performance model. And then we also have modeling of graph neural networks. So different architecture, which again used in science. So yeah. But again, every case you would have to build in and do the analysis. So it's not cheap to do that. Okay, so that's that finding there. But then this is a very difficult to interpret plot, but it's just to show that you can also expose bottlenecks and optimal parallelism. So for example, here, as I said, what we're doing is going through all the possible combinations of parallelism you could use. And then you can find that at different scales, you might want a different combination, and that might affect your memory usage, which is why you choose it. So you can actually fit in the memory on GPUs. But then that will also change your bottleneck. So you can see, for example, that most, increasing amount of time is spent in these things called pipeline bubbles, for example. So this is if you use pipeline parallelism, then you have the fact that things don't all complete at the same time. You have what's called a bubble, and that can sometimes dominate the time for the optimal configuration. Okay, so anyway, again, you should play with the tool to experience this, and hopefully I'll share the slides as well, so you'll have this information. Okay, so just bringing this together, we've seen that there's all these requirements that lead to kind of what you would want for your next generation AI infrastructure. So we have that performance modeling that influences what we need, but we also see there's like demand that's different across traditional science codes for CPU and GPU, and that there's also a desire to run simulations along with AI. So we want to build an architecture that works for that. And then things I didn't talk about, there's also a move to kind of productionizing AI for science. So things like MLOps and really having platforms that work. So we kind of built that all into, Doudna, which hopefully will be a system that provides this. This was announced in May 25, earlier this year. We were lucky the Secretary of Energy was visiting. We also had Jensen and Doudna herself, and Perlmutter also came. So this was like a fantastic event. We're trying to build infrastructure here that's really integrated AI for science. So that means that it supports large-scale model training and fine-tuning, but also a workflow that can build this into simulation and data. So the actual architecture of Doudna, if you're interested and you haven't heard, it will be based on Vera Rubin GPUs. So that's actually the generation after Blackwell. So in that plot, it should be even better than the Blackwell line. We have a high-speed network based on InfiniBand. So this is a machine with Dell as well as NVIDIA. We have high-performance storage. And then we also have CPU nodes, but also these workflow environment nodes. So this goes more to the MLOps kind of thing. If you want to run services on the platform itself, we'll have capability for you to do that. And then on top of that, we're kind of building a lot of software aspects. So this kind of just says that, really. So I won't go through that in detail. But as I was kind of indicating here, we're also looking ahead beyond NERSC 10. So, we've really seen this growth in AI and also the integration in AI with simulation. But for NERSC 11, we're really going to have to go beyond MORS to achieve computational advantage. And I think part of that is actually making the best use of the resources you have. So this is like workflows running seamlessly. I think AI also has an important role to play there. I mean, if you can accelerate simulations 10,000 times, I mean, that's obviously getting you beyond, what the compute you can currently do. But I think really to achieve that, it has to become pervasive. So that really means that us being able to enable AI wherever it's needed. And then we're also looking at things like quantum computing that I don't talk about at all here, but we have a little quantum team now in NERSC as well. So we're really looking at the feasibility of deploying a real quantum machine for the broader workload in 2030. Okay, so just to give a kind of high-level overview what we mean by an infrastructure for pervasive AI, I think there's important aspects of the system to do that. There's a variety of accelerators that can be used. I think it's also important to build AI into how we run the system. So we're looking at AI for operations, so self-driving systems. A key piece is building out this service platform so that allows people to integrate AI models, host them, and apply them to their data sets, and increasingly use like these agentic interfaces to compute and even to how they do science. So like running simulations and AI kind of together in an agentic workflow. I think it's very important to stay connected with the applications, and I think there's a huge amount of work still to do there as well about how do you actually have models that transfer across domains or even within a domain. I mean, I think that's pretty poorly understood. It's kind of a little bit ridiculous that you have to mess about with all this model and data parallel that I talked about and use a performance tool in order to do that. So it'd be great if you could scale up without going through all those hoops. So I feel like there's real methodological improvements that could make everyone's life easier. But then, putting this all into an ecosystem with support, like we always try and do, both human and AI-driven expertise. So we've been thinking about this for a while, but I just wanted to draw your attention to now Department of Energy is actually actually investing in AI for science. So this language appeared in the big, beautiful bill that was passed earlier in the year. So asking for curation of scientific data across the DOE, self-improving artificial intelligence models for science and engineering, and this idea of an American science cloud, which I can't say without scare quotes and the word American, but really trying to build an infrastructure is what that's about. And this came out with 2 calls for not a small amount of money. There's like 130 million for both of these, and that's only seen as part of the start of a program. We at NERSC, LBL is involved in both of these responses to this and the awarded. So these have now been awarded, and NERSC is involved in American Science Cloud, and we actually have a logo as well to go with it. So it's really happening. So I don't have anything to show about that, but maybe the next time I give a talk, we'll be able to describe the architecture we're building out for the American Science Cloud. Okay, but then kind of related to that is like, how do we actually make use of data and make it AI ready and build benchmarks upon that? So here again, I'm going to talk about a specific project, the Fair Universe project. I didn't put everyone's pictures here, but this is a large collaboration with lots of different institutes. And we've put out 2 competitions, one of which is live now, Cosmology competition, which is actually with Urosh and Biwei, who used to be here and is now IAC. So the FAIR is an acronym used in like data management for findable, accessible, interpretable, and reusable, I think. Although I always probably get it wrong when I say it. And so it's a bit of a pun on that because it's both fair, but then also unbiased, because as you'll see, our competitions are about the being unbiased in the presence of systematic uncertainties. So yeah. Well, it's just a name of a project, really, but why the universe? Oh yeah, well, there isn't really a relationship between FAIR and universe, but all the projects are around particle physics and cosmology, so that's the universe path, and that's the FAIR path. But yeah, the words don't really go together, I guess. But
I also think we were talking about this morning, that for the second competition, it's currently being led by an agent.
Oh yeah, yeah. Well, so it says. It would be interesting to see what their actual model is. Yeah.
Right.
Yeah. So I mean, so just taking a step back, we have vast data sets in science. So if you think about 2 projects in the high energy physics space, the Rubin Observatory, which came online, earlier this year and took its first images in June, I think, 2025. And then the Atlas detector at the LHC. I mean, if you think about the data rate of these, potentially you could say this was a zettabyte experiment, but obviously a lot of that is thrown away immediately. But even at the data kept, it's like exabytes of data. But all that data isn't really that usable for machine learning researchers wanting to kind of develop new machine learning methods. So I think there's an important effort, really, if you want to push the boundary of AI and science, to make these data available in the form of tasks and competitions that people can understand. And so one example of this was, in fact, this Kaggle challenge on Higgs, which was like over 10 years ago. But this was actually done, so this was the most popular Kaggle competition at the time, actually, but it was in a world just slightly before deep learning took off. And so it was a very much smaller data set that was used. So AI has certainly changed since then. And also the physics has changed, because now Higgs analysis have become much more precision experiments. So it's much more important to get a handle on uncertainties and systematic uncertainties. So the Fair Universe project is, aiming to build an unbiased data benchmark ecosystem. So this is both provide a large-scale compute platform that can host data sets, train models, and host benchmarks. So obviously you can tell that NERSC is going to be involved in that. But then organize challenges and benchmarks focused on minimizing systematic uncertainties. So we had a challenge last year at NeurIPS in 2024, and in this year's NeurIPS, the dataset paper related to that is out, which also shows the methods. I'll briefly describe that in a minute. But then we have a challenge open now as well. So yeah, it's this one that the agent is leading, and I'll show the leaderboard in a minute. Not actually the methods, because I don't know too much about them. So just to talk about the platform for a minute. So we built this on top of this tool that already existed, CodaBench. So this was initially a project with Microsoft and Stanford, and now is mostly led out of Paris-Saclay. and it's a community tool. It's hosted over 500 competitions, and many NeurIPS challenges use this already. The kind of unique features of this, one, it's completely open source, so you can actually, even the platform itself, you can deploy on your own resources. But it also allows competition participants to actually submit code, which is useful if you want to like benchmark the method and how effectively it runs. It's also good for reproducibility. And the organizers of the competition can define a custom scoring function. And the backend, which is useful for the integration of NERSC that's coming next, can be run on different compute resources. So we brought this to HPC. So this is a kind of architecture where you submit generally to the cloud platform that is CoderBench, but you can actually pull to run at Perlmutter. And we use this container runtime. So the competition organizers in these competitions can define their own container that is the running environment for the competition. And then we can run those at NERSC in those container. And this allows parallelism in various ways. So for example, you can run now methods that require more than one GPU. You can have many participants running in parallel. I mean, this tends to be serialized. So if people run lots of workloads on the traditional backend, it's kind of serialized. But also for the Higgs challenge in particular, we wanted to run lots of different pseudo experiments, which I'll come to in a minute. And so you can also evaluate over those at the same time and actually do statistical analysis of the variation of performance. And then, so we do this using a service architecture that we have that sits on the side of Perlmutter. Okay, so just to describe this Higgs challenge that we had last year. So this was very much an extension of the Higgs Kaggle challenge. So, you know, many of us were organizers of that first one. So this is a two-class classification problem, again, signal and background. It's a data set of 28 features, but we built a much larger data set, including lots of different backgrounds that weren't included in the original data set, and then introduced systematic uncertainty. So you can kind of vaguely see on this plot on the right that as you vary the systematics, the shape of these distributions changes. And then participants not only had to predict, so previously it was really a classification problem. They just predicted signal and background classes. Now we ask them to predict a signal strength, which is, you know, basically the significance of the signal, but also an uncertainty on that. And then we run it on the back end on multiple data sets, and we expect that the interval that they predicted, one should be as small as possible, but also it should actually contain the correct mu 68% of the time if they provided a 68% interval. And then we combine that into a single score combining both interval and coverage. And this plot on the right just shows that the coverage score, as you increase the size of the data set, gets narrower. So we kind of expected that we should see the expected behavior that they get a tighter coverage with more data. Okay. And then I'm not going to go into detail what happened. We had a competition and we got various entries. I think what's interesting is that out of the top 3 participants, 2 of them weren't directly in, so these 2 weren't directly working in particle physics already. And in fact, the third participant didn't have any knowledge of particle physics at all. So that was nice to see. I won't go into detail of their methods. This team, which was in particle physics, really used a method that's kind of similar but extended from what particle physicists normally do, this like log likelihood based method, but an unbinned version. Whereas this other student we had who we're now working with, actually after he won this competition, we hired him as a graduate researcher, and so he built this contrastive normalizing flows option. But you can read about this in the dataset paper. Perhaps more interesting is the current challenge. So this is a weak lensing challenge. So weak gravitational lensing as a problem is about you know, distant galaxies kind of get distorted by matter in between, and this is like a statistical effect in weak lensing, and so you can you know, really see long range, you know, the large scale structure of the universe through weak lensing. So we have 2 phases of this. The first is parameter estimation. So this is really a regression problem on 2 parameters, cosmology parameters that went into the initial simulation. And then we expect to have a phase 2 that's really about that's out of distribution detection. So this is really finding anomalies, a much harder problem. So the competition is there. Oh, just to say a bit about the data sets. So these are simulated data sets, you know, mimicking observation from the HSC survey for 101 different versions of these parameters. the actual data that you're looking at is a 2D image, which corresponds to like what's called a convergence map in the field. And again, we're applying systematic uncertainties, two baryonic ones and one photometric. These are actually produce different simulations, so they're actually separate data sets. And then pixel level noises, where we give people a tool that they can vary this to apply different levels of pixel noises. And we provide some baseline methods, again, like the traditional power spectrum that's used in the field, and a convolutional network, either with MCMC or directly trying to predict the uncertainty from that. And again, there's much more details on the competition site, but you do have time to enter and win. And so this was as of earlier today, you have 9 days. This was the one people were referring to, this apparent agent from a Cambridge team, I think. This one is actually Francois Lenous's team. And they actually made this dashboard as well, so kind of visualize it. So you still have time, so enter that. Okay, so then I'll briefly conclude, and we might have a minute for questions. So I think really over the last decade, this modern AI for science has kind of demonstrated a potential to really change the field, and it really benefits from the existence of large-scale data sets. Benchmarks, I think, are really important. Also available compute, so we tried to help there with NERSC, but we should also make it performant. And I think, again, these combined teams of bringing people who actually know how to train models at scale with domain scientists. But there's work still available to fully exploit. We're kind of available, and do get in touch if you want to collaborate. We are building our next system, so there should be a step up in resources available. But I think this DOE investment, this is what I'm talking about in this last bullet, I think will be really important to bring together the community in different domains and build an architecture that works for all of them. So yeah, thank you.
We have time for questions.
So first question relates to the work that I think that Bhimji was studying.
Yeah.
I mean, you said that you are learning the representation through the whole process. What do you mean by learning the representation in that project?
I mean, I think it's just,
because you were using the GNNs together, so I was just like,
yeah, I mean, I guess it's not so much an explicit recommendation, but representation. But I guess the idea is that the model sort of encodes the representation. Like, yeah. So it's not quite like some other projects in other domains maybe use the embedding as a kind of representation that's used for other downstream tasks. I guess it's not as explicit here, but I think that's what I meant. Yeah.
My second question maybe is like, how can you get a tour through NERSC?
Oh, tour, yeah.
I'll say that we can take a tour.
Yeah, well, he managed to get on a tour. Well, you can contact me if you want. Yeah, I mean, there is a public page where you can go and request a tour, actually. Yeah, so I don't know, you could let me know if that doesn't work, but I've always been told that there is such a public page, and we do sometimes get public tour requests via that, but it's probably easier just to contact me directly if you want to. Yeah, are you working up at the lab, or?
Yeah, I have affiliation.
Okay, yeah, so if you already have a badge, then it's trivial. Yeah, we can give you a tour anytime.
I had a question. So
Yeah.
in the last sections of your talk, you elaborated a little bit about uncertainty quantification. I mean, I think this is an area where, like, at least in the physical sciences, there is kind of a distinction from what industry is maybe going for, and that we really care about well-calibrated, predictions. And so, on the one hand, I mean, you can use a neural network to like predict an uncertainty, like maybe alluding to, but there's also all this kind of machinery that's been built in terms of kind of like the backbone of Bayesian inference through like samplers of various sorts. And so I was just curious what your perspective was on this, and whether you view these as kinds of separate entities, or something that would motivate more synergy at the level of infrastructure.
Yeah, I mean, I hope that was part of the goal of this fair universe in general, was to promote more synergy. So I would say, I mean, industry is a little bit interested in these. So some of our collaborators, like Isabelle Guillon, who was like, is a machine learning researcher, now works for Google, was interested in industry applications as well. So for example, image recognition in low light is kind of a little bit similar to some of the problems we have. So I'd say that there is some interest from industry, but it is definitely a problem that, you know, we really need a solution to. There's kind of multiple aspects. So there's one is like the uncertainty of your machine learning model itself. So where you would like run experiments with different dropout. There's all kinds of different ways of doing that, or use Bayesian neural networks or some approach like that. And then there's being robust in the presence of systematic uncertainties, which was very much what our first competition was centered around. So how do you have like something that's optimum even in the presence of systematic shifts, where you might do things like data augmentation or decorrelation or other couple of things. Yeah, but I would say, yeah, these are all related. So it would be great. I mean, through this, we had a couple of workshops on the topic, but yeah, it would be great to have a more systematic, no pun intended, yeah, we have categorizing things, yeah.
So is there an insight in which direction is it mostly data distribution so that the model is like in sense, or is it the model itself distributed?
Yeah, so there's a variety of methods. So I mean, basically, yeah, if you wanted, I probably should have said, if you wanted one conclusion from this, I mean, basically you should use data parallel, which is splitting the data across nodes as much as you can, right? But in some cases you can't do that. For example, your model doesn't fit on a single GPU, so then you have to go to using multiple GPUs. Yeah. Yeah. I mean, I would say both. And so, I mean, definitely data parallel is the more prevalent use case. So that's the most important thing to support. But we do see people who don't fit in a single GPU, or they're using, so we have both 80 gig A100 GPUs and 40 gig A100 GPUs, but we have a lot less 80 gig GPUs, and people are still waiting in the queue to use an 80 gig GPU, right? Where they may, you know, if they had a simple way to use multiple GPUs, model parallel, but, you know, it often requires all kinds of hoops. So if we can provide, and there are easier tools now, like there's this, for transformers at least, there's Transformer Engine now in PyTorch. So there are improvements on the software side to make it easier, but otherwise, yeah, you know, it's handholding. And then people show this interesting plot where you see the size of model compared with the size of memory on the available NVIDIA GPU at the time, and you see those jumps. Everyone's trying to fit on one GPU and limiting themselves by that. So if you make it easier for people to run across multiple GPUs, then they're not restricted in their model sizes. So.
Oh,
yeah.
Is that it?
No. I was gonna.
Thank you for this amazing talk.
Oh, thanks for saying that.
Tangential
Oh.
about. I just want to put in a plug. I can only say this because he's not here for Yagi.
Oh, yeah.
NERSC 11.
Oh yeah, thanks for saying that.
Thank you.
Yeah.
I was
Yeah.
wondering if there were any questions on the Zoom from anybody. Do you know?
Yeah.
If anybody on Zoom has questions, you
Oh,
can
yeah.
raise your hand, or
No, sorry. Yeah.
we might not, but
I can't.
due diligence. Thank you. Okay. Yeah. Well, I mean, yeah, we have the benefit of Wahid being local, so I encourage you to
Yeah.
reach out if you have further questions. But yeah, let's thank him again.
Good.